This begins EE555 discussion on Wednesday, March 26th, 2014.
Okay, good morning everybody. Today we'll talk about BGP, and in the second part we'll see some examples of routing tables. Alright, so let's get started with some simple program in BGP just to wake us up. And so problem number 1, consider the following network. ISP-B provides a national backbone service PA. We have ISP-B here and ISP-A. Provides national backbone service to regional ISP-D, C, and regional ISP-D. Each ISP consists of them B and C pair with each other in two places using BGP. We have two pairing points, okay?
The time is 6 o'clock.
And consider to D. We want to send traffic from A to D. Prefer to hand the traffic over to C, obviously. I mean, I don't know if it's obvious, but usually people want to give the traffic to other networks because they pay, for example, per traffic or something like that. Okay? On the west coast, this B would prefer to hand that traffic over C, B, and he wants to hand that traffic to C on the west coast, here. Why? If the traffic comes here, then it will cross the country from this side, right? You want to send the traffic over here in order to cross the country in C's network. While C would prefer to get traffic via its east coast pairing point with B, but B would have carried the traffic across the country. What BGP mechanism might C use would hand over A to D traffic at its east coast pairing point. That to answer this question, you will need to dig into the BGP specifications. So the traffic from A to D, and we want the traffic to travel. If we focus at which one? Where is it? What we are at C. Okay, so we want to see what policy C will to send all the traffic to the other guy. So how this can be, any ideas? Think about it. We don't really go to much BGP details because it's a complex protocol, so let's use some high-level idea. Okay, so if you are C, you want the traffic to travel over B's network. If B knows that there is a router, right, if there is a route here, he'll send the traffic from A from this link, in which case that needs to cross C's network, but C doesn't want that. So the idea is that C will not advertise, the pairing point is known, but the route to D is not known, right? The point is that C will try to hide or it will advertise only reachability to autonomous system in ISP-D. Okay, that's the idea. Now, it's reasonable to ask, is this enough? And the autonomous ISP will not realize that it's being, cheated or something? The answer is that in real BGP implementations, this is possible to see, if, but in any case, in a simplified scenario, we can assume that if you limit your advertisement to something, you can game the system. Okay? Make sense? And what else I want to say here? And of course, even if you are ISPC, you can even define different weights. In reality, what they do, they basically configure the weights such that the link costs, such that they push traffic from one. Okay? All right. So let's quickly write down a short answer for that. So the answer is that C is route to D. To D via its east coast peering point. And of course, if you specifications of the protocol, you'll find even more details how this can be done and things like this. So let's go to the next problem. Do you have questions here? Okay. Problem number 2. In the following figure, I have the figure here. I hope you can see that. You suppose that there is another stub network B that is a customer of ISP A. Okay? We have here, we'll see who is a customer of whom. Let me okay. The relations. Suppose that there is another stub network B, ISP A. Suppose that B and C have a peering relationship. B and C are peers, and A is a customer of C. A, customer of both B and C. Suppose that A like to have the traffic destined to W, A, the traffic destined to W, to come from B only. So the traffic goes, and the traffic destined to V from either B or C. So we want to allow both B and C to carry traffic to V. How should A advertise its routes to B and C? Autonomous system routes do C receive? First of all, what is a stub autonomous system? A stub network? Do you remember?
It won't carry traffic for us.
It's only either it's coming from this network or it's going to this network, right? Okay. And also you can see that it has only one link over here, right? Okay. The question is, as we said, suppose that A would like to have its traffic destined to W to come from B only, and the traffic from either B or C. What will we do now? Again, it's a problem of how you, okay? Any ideas?
You will not advertise the route AW to C.
Correct?
And you will advertise AW and AB to B.
There you go. That's it. Okay, so the answer is that like this. A will advertise B two routes. A to B AW and A. Okay, and also A will to C1. This is which route? AV. And what is going to B and C? B and C now exchange. Basically, how should A advertise its routes to B and C? That we answered. What autonomous system routes do C? So C will receive some information from B too, right? Also, B will advertise to C two routes. Which routes? The logic is whenever an autonomous system gets a message, a BGP router, it's what? Right. It's at the path, right? It's ID. So in this case, what is going to happen? We have at B, what kind of paths? AV and AW, right? And also C, a path, AV through A. So, okay, so we have two routes. One is B. This is at C, right? And the other is what? BAV, right? Okay, so how many routes does C? 3. It's a total of 3 routes. Which is AV, BA, and BAV. Oops, sorry. Okay? If you want now some analysis, I don't know if you feel comfortable with what, you can look it up in Ross' book. They have a high-level description, and these examples are also taken from there, I think. Yeah, go over it. It's a very easy to read, you know, and maybe you can go over other books too, and the notes, of course, of the professor, just, you know, to feel more comfortable, because it's really a very complex protocol, and what we say over here is very, very like high level. Because there are complex customer relationships between autonomous systems. You have how you send traffic, you know, through another network and things like this. Okay, any questions? All right, let's go to the next one. Those were easy problems. And easy too, I think. Have you taken 450? Okay. So I want you to answer to this. So problem number 3. Consider a datagram network using 32-bit host addresses. The router has 4 links numbered 0 through 3, and packets are to be forwarded to the as follows. So you have 32-bit addressing. What else over here? Okay. So we have destination address range phase. That's the mapping, okay? So the address that starts, I'm not going to read the whole thing. This address range goes to link number 0. The second is an address range, right? Don't, you know. Goes to link number 1. We have another description that goes to 2, and all the rest go to 3. Is provide a forwarding table that has 5 entries, uses longest and forwards packets to the correct link interface. So what is this prefix matching? can you repeat your answer?
So like, you just mentioned the longest destination address is not appear on the range of the prefix on the associated sign to otherwise.
Okay, yeah. And if we have, let's say, if it matches two prefixes, then two networks, then we will take the one with the longest prefix, right? That's the matching. Because we want to break down. Okay. So now the idea is, we have some address space. Okay, that's how you design a routing protocol for a routing table. So we want to describe those ranges using routing rules. Down. It says 5 here. The fact that it says 5, it seems like we can't, or in 4. Why? How many would we need minimum? So it seems like we can't express maybe a one rule using just, direct mapping between what we have and the link interface. So let's analyze one of its of all those ranges. First of all, what range is this? It seems like it's all the numbers from here till here, right? So space, let's see what happens in the second one. The second one starts right after next number exactly, right? 100, it's 111 till here, then 1000. I don't know which number is, but we don't really care. Okay? Do you agree what I'm saying? Do you understand? So we don't have any gaps between the first and the second range, and the second range, it doesn't go up to 111 all ones after this digit here, right? So 111 over here. So I think you will tell me, but I think we can even here describe it using fix, right? You will tell me what it is. And the third rule, something different happens now. So we start after this number over here, the 1000111 till the end. We have 1 zeros to the right. We go up to, instead of going like this, the way would be to go up to all ones and the rest are 0, higher, okay? So this might be a bit problematic. You agree? Okay, so now let's see how we can convert that. So okay, so what is the prefix? Start writing a table here. Prefix match link interface. First, the address range. What will be the prefix match in this case? Till when? Right. 8 plus 2, eh? Okay. Why? Because with this rule, imagine that with a single line, we want to characterize all the complete carding, let's say, the rest. Right? You put a star, you know exactly who is. Agree? So the first prefix match will be 111 0 0 0 0 0 4 0 0. Okay? And we go to link interface. Okay, great. So what about the second one? The second 16 digits, 16 till here, right? Perfect. We have all the numbers to the right. So the second will be, I'm gonna 1 1 1 0 0 0 0 0 0 1 0 0 0 0 0 0. Goes to link interface number 2. I'm sorry, 1. Let's see the third one. Any ideas for the third one? Separate. That's a good idea. So what will be the range in this case? First of all, we can break it down into two things. One is theoretical, I don't know about this case, but either you can break it into two ranges, like say, okay, this and this, no, we're talking about the link interface 2, right? So we can break the other space for 2 into 2 chunks, such that together we take 2. Or longest prefix matching allows us to do what? Thing more generic with a less number of, a smaller mask, and then longer match, subtract whatever doesn't belong to this particular range. You see what I mean? Because longest prefix matching can be used here for that. Theoretically speaking, we could say, okay, send whatever starts from 1 and the rest I don't care, send it to 2, but use longest prefix matching from this generic statement or whatever you don't need. That's what we need to apply here. So if you want to do what I just said, how would you do it? Look at what happens over here. 7 digits. So 7 digits, why? Because the 8th digit in this particular range will be either 0 or 1. So we want to send everything that 111, 0000, 7 digits, we say 2, except whatever we don't want to send to 2, which it should go to 3. So let's write the third rule, which is the 1110, 00, and that's it. It goes to link number 2. What do we add by using this generic prefix over here? Which cases we don't want to include in this case, but we still add them? To me, it seems like something is happening over here, right? It's the cases that have 1 and don't care in the rest. Do you agree? Why? Because if this was 1, we have all the continuous number of addresses, that's fine. But, combined with prefix that we just said. So we need to subtract everything that starts with this prefix and all the possible combinations to the right. In other words, we need to subtract, by subtracting out it to interface 3, whatever starts from 1, 1, 1, 0, 0, 1, and then, okay, and this goes to 3. Have we specified everything now accurately? I think we have, right? And then we can have another rule that says otherwise 3. Okay. So how many entries do we have? 1, 2, 3, 4, 5, and that's all we need. You can come up with something else, some other, breakdown, but longest prefix matching helps us here, the way. Okay. Now let's go to part B. Describe how you're forwarding the appropriate link interface for datagrams with destination addresses. So let's see. How would do you see it? Assume we have a datagram with this address here. Where is it going to go? It's going to 3, you said? It's 1100 anywhere. Do you have a, if you want to be really exact, you should do the logical end, right? And then you'll select the longest prefix. We can usually do. This is a very easy case because we have 1, 1, 0 over here. Do you have 1, 1 rule that says something that starts with 1, 1? No, only 3. Only the otherwise catches that, right? So, I'll say it, maybe I'll say number 1. It matches the 5th entry. Oh, I'm sorry. Okay. It matches the 5th entry. The second case is this. 1, 1, 1, 0, 0, 0, 0, 1, 0, 1. So which one is this? Right? Why not this guy? Or why not this guy? This differs first of all. Right? We have 0, 1 and then it's different. This is generic enough, and the first one differs again. It differs, right? So the matching will be with the third it matches the third entry. Okay, and the last one? Which one is that? The 4th entry. Why is that? Do we have another that matches this? Not really, right? 1, 1, and 1, we have the same, like the 8th digit is 1, and then the next is 1. And this happens in this case only. Okay, so the third, it matches the 4th entry. So it will go, first let me add the interfaces here. The 5th is interface, I mean by that, right? I-phase 3, interface 2, and interface 3. Any questions? Right? Okay. That's kind of a revision of what we have seen in 450, I guess. All right, so let's go to the problem number 5, network using 8-bit host addresses. Suppose a router uses longest prefix matching and has the table. Prefix match 0, 0, interface 0, 0, 1, 0, it goes to 1, it goes to 2, 1, 0, 2, 1, 1, 3. We have 8-bit, it's okay? For each of the 4 interfaces, give the associated of destination host addresses and the number of addresses in the range. Let's wake up, guys. All together. So, yeah. We have 8-bit hosts, have this prefix match, and then for each of the 4 interfaces, give the associated range of destination host address in the range. So, problem number 4. Let's create a destination address range, right? And then link interface. So what is the address range that goes the prefix match? Talk to everybody over here and see if they overlap and if what's going on, right? But it's the only one that starts with 0, 0, and that this will kind of match packets, or starting basically from which address we said, all zeros, right? 0, 0 through what? 2, 0 all ones, right? And all these will go to link interface 0. About the next one, 0, 1, 0. 1, 0, it will take what? 0, 0, all zeros, and then it will go 0, 1, 0, it has to be like that, and all ones. And this will go to the third one is 0, 1, 0, 1, 1. Make them look like pairs over here. 0, 1, 1, and then all zeros. So another that's doing the same, no. Through what? 0, 1, 1. 8, okay. And this go link number 2. The next one is 1, 0. Okay, 1, 0, obviously 0, 0. It goes through what? 1, 0, all ones. Okay, and this should go to 2 as well. And the last one starts 1, 1, all zeros, goes up to 1, 1, 1, oops, sorry, all ones. So this will go to interface. All right, so I think we have all the exact ranges over here. So the next question is, we gave the ranges, the number of addresses in the range. So how many addresses we have in each range? Okay. Let's call them the number of addresses in the range. Okay, let's call this guy 1, 3, 4, 5. So, I mean, that's very basic, right? So 1, how many? How much? 2 to the power of 6, right? 6, which is 64 addresses. Okay, number 2. It's 2 to the power of 5 is 32. Number 3, we have 3 digits here that they don't change. The rest are 5. 2 to the 5th equals 32. Number 4, how many? 6. Number how many? 2 to the power of 6. 64. Okay, great. Now, how many go to each interface? Can you repeat that? Oh, let's see. Interface 0 gets addresses from 0 only, right? So it's interface 1, 32, we just found it. Interface 2, right? We just sum the two that go to, yeah. And the last, 64, right? That's all. Oh. For first time in history, we finished a little bit earlier. Now, do you have questions on that? Okay. Do is, if you want to refresh your knowledge about this, just go over, routings and stuff, and then I would recommend you go over BGP from the textbook details, right? Okay, guys. So thanks a lot.
And this 5 discussion on Wednesday, March 26th, 2014.